Hi everyone and welcome back to my channel. In this video we'll be talking about insertion sort. Given the list of numbers on the screen, if we were to use insertion sort to sort it in ascending order, we would move each number to the right if the number to its right was greater than it. So our first number, considering just 3, we do nothing because it's a trivial case. It stands alone, and if there are no numbers after it, then it's already sorted. But we have 3, we have 4, which is already sorted, and then we have 1. So using insertion sort, you want to move 1 over here and then move it again over here. So you move 1 here because 1 is less than 4. And when you have 3, 1, 4, 3 is also still greater than 1. So you move 1 before 3. So at this point now we have 1, 3, 4, 8, 5, 2, 6, 7. So this is how you move numbers in insertion sort. Now this seems correct, 3, 4, 8. But then we have 5. So it means we want to move it here. And by the time we move it there, we have 1, 3, 4, 5, 8, 2, 6, 7. So we have 1, 3, 4, 5, which is sorted. And here we have 2 after 8. So it means we are going to move it from here. We move it here. We still move it here. And we move it here and here. And then would have 1, 2, 3, 4, 5, 8, 6, 7. And we continue like that with just in the same way with 6 and 7 until we have a sorted list of numbers that goes from 1 to 8. So we'd have 1, 2, 3, 4, 5, 6, 7, 8. So this is sorted. So that's how insertion sort works. So now let's put down what the pseudocode would be if we were to write an algorithm for insertion sort. So this is what it will look like. So for our insertion sort algorithm, where we have an array of numbers, let's call it A, that goes from 1 to n, our pseudocode will look like this. So for I, this is what our pseudocode will look like. For I equals 2. So I is positional. So I equals 2 would be the number here at this point where I just added a dot. So for I equals 2 to n, these are positional. So for numbers at I equals to here all the way to n, let us call, for each number we pick, let us call it j. So j is equals any I that we pick. So while, now we are going to have a while loop. We are going to say that while j is greater than 1, while j is greater than 1, so this is positional as well. So while j is greater than 1, so the positional at 2 is greater than 1, right? Because this is 1. The first number is 1. The positional at 3, the positional number at 3 is greater than 1. So while j is greater than 1 and aj is less than aj minus 1, we are going to swap. So we swap aj minus 1, and then our new j becomes j is equals j minus 1. So my whole thing is trying to break this whole thing down just so that it makes sense to everyone. So let's write down our numbers again. So let's say, for example, we have let's say for example we have an array of numbers. Let's say 3, 4, 1, 5, 6. So This is an array of, random numbers. So let's follow what this algorithm says. It says for I equals 2 to n. So this is I equals 1, I equals 2, 3, 4, 5. So these are positional numbers for the numbers in our array. So this means that for the number at position 1 we have 3, the number at position 2 we have 4, number at position 3 we have 1, number at position 4 we have 5. So that's how you interpret that. So for I equals 2 to n, so for I equals 2 to n, this is 2 to n. What? For I equals 2 to n, this is 2 to n. J is equals I. So let's start with the first one. J is equals I. So let's say J equals 2. Right? So while J is greater than 1 and AJ is less than AJ minus 1. So J is greater than 1, as you can see, because right now in this instance J is 2. AJ, A where J is 2 is equals 4, because at positional 2 the number is 4. Let's see whether it is less than AJ minus 1. So J, in this instance J is 2, right? 2 minus 1, that's 1. And A in positional 1, that's 3. So let's see. So is 4 less than 3? No, 4 is greater than 3, so we leave it as is. We don't have to swap at this point. Okay, so let's go to the next one. J equals 3. Let's go. Let's say J equals 3. Let's say J is equals 3. For J equals 3, let's see. J is greater than 1, which is correct, and AJ here is 1, less than AJ minus 1. J minus 1 in this case will be 2. So A2, right, will be 4. 1 is less than 4, so we swap. So that means we are going to have, when we swap, we are going to have 3, 1, 4, 5, 6. And at this point, we change our value of J to J minus 1. So that means we're at the point of our swapping, our J is equals 3, and new J is going to be 2. So J is equals J minus 1. In this case, it's 2. So we repeat the whole process again. So if you repeated this whole process again and again and again, we will end up with a sorted list. That's a sorted list of numbers or array of numbers going from 1, 3, 4, 5, 6. So I hope this is pretty clear to you. Okay, so now that we have written the algorithm for insertion sort, I think the next thing we'll do is to write a proof for insertion sort. So let us start with induction. So using induction, we're just going to write a simple proof by induction. Our base case, remember, so this is our proof by induction. So let's say part 1 is, let us call this proof by induction. Proof by induction. So let's grab our base case. So we have, of course, an array of numbers. Let's write it by the side. Let's say we have 1, 2, 3, 4. Our base case would be, because our first number, let's call it 1. No, just let's say 3, 4, 5, 6 would be our number. So our first number is 3. In our base case, if 3 stands alone, it has no other number, compared with it. So we can say that 3 is already sorted, right? So at the start, this is our proof by induction. So at the start, we can say that at the start, our positional number at A1, this is 1, is already sorted. It's trivially sorted. Like I said, if we had only 3 standing alone, it has no comparison, so it is sorted already. But let's move to the next one. Positionally, we have 1, 2, 3, 4. So we have the number at position 2 is 4. So in iteration, let's say where I is equals to, and in this case where I is equals to, we have 4. The algorithm compares A2 to A1. That's the first step. The algorithm compares A2 to A1, and if, going back to our pseudocode, and if the number we have here is less than, if the number at A2 is less than the number at A1, we swap. If not, it's already sorted. So let's get back. So here, after that comparison, just like I said, you should write that down. If A2 is less than A1, we swap. If not, it's already sorted. So, and if we swap, whether we swap or we leave it at that based on whether this is less, it means that what we have at this point is already sorted. So therefore, this is like a therefore, all the numbers from this to this is then sorted. So this, everything that I've talked about here, is our base case. Okay, so that also means that by induction now, so let's take by induction now, what we are saying is that if we introduce another number into our array of numbers, now we are also going to check using algorithm, just like it's stated in the pseudocode. We are going to check if the numbers by the right are greater. So positionally, is AJ less than AJ minus 1? So if we introduce a new number here, let's say 7, yeah. So and it's at position 5. So by induction, we are now going to check, is A5 less than A4? So this is assuming that the numbers from A1 to A4 are already sorted. If you introduced another number, you'd then check, is the last number you just introduced less than the number before it? So instead of using 5, let's use, so let's call this, instead of 7, I just wiped something, yeah, instead of 7, let's call that n, right? Let's say that this is n. So now we are going to say, is the number at an less than the number at n minus 1? Or, I mean, you could say this is something as saying, if you call this n plus 1, so it means that this is n. So this is something as saying, is the number at n plus 1 less than the number at an? So this is what the inductive step is asking. So if this number at n plus 1 is less than the number at an, you swap and check again. Then you keep swapping until everything is sorted. But if it's greater than the number at a plus n, given that all of the numbers from a1 to an are already sorted, it means that your list is sorted. So this is how you write the proof by induction. All right, let's write this same proof by contradiction. So this is what the proof by contradiction would look like. Proof by contradiction. So by contradiction, we want to prove that if we are given an array of numbers and the algorithm we've used to sort them didn't really sort them, then it did not follow the insertion sort algorithm. So that's just what we're trying to prove, that the insertion sort algorithm always produces a sorted array. So for the first one, we are going to assume the opposite, and what we are going to assume is that this array going from 1 all the way to n plus 1 is not sorted. let us assume that this is not sorted. And if this is not sorted, what it means that there'll be two cases. What it means is, this is what the first case would be. Case 1, what this means is that there is an AJ. Hold up. What this means is that, what this means is that there is an AJ less than AK for some K less than J. So I'm going to prove these cases with, numerical examples that have like numerical numbers, just so that it's clear. So what this is saying is that, let's use an example. Let's say by the side, let's say that we have these examples. Let's say that we have this array 3, 4, 5, 6, right? 3, 4, 5, 6, 7. So for the case 1, we want to say that we have an additional number 2, right? Normally, if you inserted in our insertion process, let's say that some algorithm sorted this number 3, 4, 5, 6, 7, 2 and ended up at 3, 4, 5, 2, 6, 7. But at the position where the algorithm has left 2 at, 3, 4, 5 is greater than 2, which shouldn't be so. So think about it like this. Think about it like this. Let's say that this is positional now. Position 1, 2, 3, 4, 5, 6. So 2 is at position 4, right? So this is the case 1. Let us say that at this position, let's call this position position 4, where we have 2. Position 1, 2, 3 is greater than the numbers at position 1, 2, 3. That's 3, 4, 5 is greater than 2. So we can say that this is case 1, and that's because 3, 4, 5 is greater than 2, while 6, 7 is greater than 2. So this position, in the way that it's been sorted, is correct, but this isn't, because all the numbers before 2 are supposed to be less than 2. So let us now translate this into this. So we say AJ is less than AK for some K less than J. So since K less than J is positional, let's translate this into these numbers that I've written here. So we're considering this number here. So let us call this K. Let us call this K. So that means all these numbers could be, any of them could be a J. So it means that K less than J. Oh, that's the other way around. All of this could be a K and this would be a J. So K less than J. So this is it. So our case 1 is that A of J is less than, so A of J, which is A of 4, as in this case, A of J is less than A of K, which is any of these, 3, 4, or 5, is less than A of K for some K less than J. So positionally, K less than J, 1, 2, 3 is less than 4, so K less than J. I'm just trying to repeat this to show how this example means the same thing with this notation for some K less than J. So this is the case 1. And why is this a contradiction? It's a contradiction because A3, oh, that's A1, A1, A2, A3 are all greater than what we have at A4. That is why it's a contradiction. But during the insertion method, we always compare numbers to the numbers, by the right. So if we compared 5 to 2, it means that using insertion method, 2 would have to move. If we compared 2 to 4, using insertion sort, which is what insertion sort requires, it means that 2 would have to move. But since 2 didn't move and it's somewhere here where numbers by the right is greater than 8, so it means that this is a contradiction. So in writing your proof, instead of writing 1, 2, 3, because this is tailored exactly to this example, you could say replace this still with K and replace this with J. So you can say this is J, this is you can call this J. Actually, you can call this any of these J's. So if you call this J, this will be J plus 1, this is J plus 2. If you called this one J, this will be J minus 1, this is J minus 2. It doesn't matter, you're just trying to explain what position this is. So if you've put this down this way, you can then combine it here to just make the statement that I made, that during insertion sort, the number A is compared with elements to it's compared to elements before it. It's compared to numbers before it. That is, so at this point you cite that expression we had in the pseudocode where we said that if this guy is less than this guy minus 1, we swap. Therefore, this case is a contradiction. So it is a contradiction, if that makes sense. Okay, so this is the case 1. My hope is that using this numerical example, you are able to translate this proof. You are able to translate it into a proof by contradiction. So this is the first case. So let us move on to the second case. Still under proof by contradiction, we have case 2. So in our case 2, what happens? In our case 2, we have that for some k greater than j, we'd have, this is our case 2, a positional k is less than a, let's say j, for some k greater than j. And as usual, let us use a numerical example to show. So this is what case 2 would look like. So let's see. Okay, so let's use still like the example we used before. Let's say 3 to 4 let's say 3 to 4 5 1 7. So there's something wrong with this. 2 is in the wrong position and 1 as well is in the wrong position. So let's see. It says AK less than AJ for some k greater than j. So let's put down positions. We have position 1, 2, 3, 4, 5, 6. Position 1, 2, 3, 4, 5, 6. So let us call number 1, which is at position 5. Let's call it K, right? This is our K. And let's call everything up to this point position. This is some position J. So this guy K is greater than J. Great. So let us try to interpret this. It says there is an AK that's less than AJ. So let's see, there is an AK, this is 1, that's less than AJ for K greater than J. So this is K greater than J, and there is an AK, this is AK in this case is 1, that's less than an AJ. So 1 is less than all of these guys, right? So if that's the case, it violates the insertion sort guarantee of placing the smallest values first. So let's put that down. So repeating what I said about case 2, 2 is placed before smaller numbers like 1. So what differentiates case 1 from case 2 is that in case 1, 2 is placed after bigger numbers. It should have been before. But in case 2 that we have right now, 2 is placed before smaller numbers like 1, if that makes sense. Because at this point it might look like we are saying the same thing over and over. In case 1, where there is no sort, 2 is placed after bigger numbers. This is 2 is placed after bigger numbers. But in case 2, our problem is that 2 is placed before a smaller number. 2 is placed before a smaller number. So that's what our problem is. And still the same way we translated this case into this one, that's still the same way you are going to, express case 2 as a contradiction of what insertion sort is. Still building it around the fact that in our pseudocode we said that if AJ is less than AJ minus 1, then we swap. And in this case, let's see, let's say AJ is less than AJ minus 1. There is an AJ in this example that is less than AJ minus 1. So it means that if some algorithm gave us this as a sorted array, it means that it is a contradiction to our insertion sort algorithm. So we have done both the induction proof, the contradiction proof as well. So let's go to the last part of this video. It's already taking longer than I thought it would. So in the last part of this video, we'll talk about the running time for this insertion sort algorithm. What's the running time? So in the worst case scenario, the running time, let's talk about running time. That's time complexity, running time of insertion sort algorithm, of the insertion sort algorithm. So what's the running time like? So in the worst case scenario, this is the worst case scenario. The worst case scenario is a scenario where we have nothing sorted at all. So we have 5, 4, 3, 2, 1, but it should be 1, 2, 3, 4, 5. So it means that nothing is sorted. So what this means that is this guy, number 4, would move 1 time. Number 3 would move 2 times. Number 2 would move 3 times. Number 1 will move 4 times. So this means I'm just going to explain how we got, because this would be an O n raised to power 2. So it's going to be a squared time complexity, n raised to power 2 complexity. But I just want to explain how we got there. If 4 moves 1 time, that's 1 plus, and 3 moves 2 times, we have 1 plus 2. 2 moves 3 times, we have 1 plus 2 plus 3. 1 moves 4 times. So our number of moves would be, if you add this, you're going to have 10. But in reality, we're not just moving numbers. We compare first before we move. So it means that we are comparing 10 times or more as well, then moving 10 times. So this means this is number of swaps. We have 10 swaps, but we also have a greater than or equals 10 comparisons, right? Comparisons. So this would be time complexity of, for n equals 5, we see that we already having a complexity of about greater than or equals 20, right? So this leads us to this guy. We have an O of n raised to power 2. Also, if you're familiar with, triangular numbers, you'll notice that 1 plus 2 plus 3 plus 4 plus 5, 6, 7, just like that, they are like triangular numbers. So it means that you could rewrite this series to this, where I minus 1 is equals n. So, and if you write this to this guy, they mean the same thing. If you write this to this guy, these are equivalent actually. It's under series and sequences. So if you're able to write this to this guy, you'd still see that this is an element of this. It has an order of n squared, n raised to power 2. So the worst case time complexity is O of n raised to power 2. But because sometimes a given list of numbers might not be in its worst, situation. So we could also have a time complexity of O, or linear time complexity, that's called O of n. And this happens when everything is already sorted. So we have 1, 2, 3, 4, 5. So you compare, but you don't have to move because everything is already sorted, right? So this is a linear time complexity. So on average, our time complexity for the insertion sort is O n raised to power 2. So so it's an O n raised to power 2 overall. Space complexity would be constant. Our space complexity is constant because we have n is equals 5. Even after sorting it would be n equals 5. So for our space, it would be constant. So we're going to end this video here. I think I've been able to touch on important parts of the insertion sort algorithms. I'll see you on the next video. Have a good one and see you on the next one.